Okay, we are good. So we're starting a new section today, equations. Talk about equations. So, let A and B be algebraic expressions. We spoke about what those were already. Okay. So some variables raised to powers multiplied by coefficients in a sum or a product or a division or a radical, something like that. So if A and B are algebraic expressions, we write A equals B to mean that A and B are the same expression. So they might look differently in the beginning, but ultimately they are the same. And if AB can be thought of as functions A equals B means that the same domain and if the same input is plugged into A and the outputs are the same. Star, because we'll discuss later. So we will be revisiting the notion of a function. So just in case you forgot what that is, we'll be talking about that later. So if you don't remember exactly what that is, we'll get to it. And so A equals B is called an equation. Because of that symbol called equal sign. If it does not have this symbol, it is not an equation. Okay? Moving on. Now here's the thing with equations, they have certain properties that are very special to expressions of this form that have this symbol, that without this symbol these properties are not true. So let's talk about the properties of equations. Now you can actually prove these, but we're not going to prove them, I'm just going to state them for you. There are four main properties that we will be using that will be very convenient for us. So, let A, B, C be expressions. 1. If A equals B, then A plus C would equal to B plus C. In other words, we can add the same thing to both sides of an equation, and it will not, and the equation will be maintained. And in particular, the solution set to this, and that will be the same. So we can add something to the same thing to both sides of an equation, and the equation will be maintained. And we might do that to simplify things and put the equation in a more convenient form. Otherwise, if A equals B and C is not equal to 0, then, well, it works even if C is not equal to 0, but even if C is equal to 0, but you usually won't apply it in that case. Then AC is equal to BC. And so you can multiply both sides by the same thing, and the solution is maintained if C is not 0. By the way, I'm using the word solution. I should probably tell you what that is. What is a solution of an equation? Let me continue though. So those are two properties. The third one is a refinement of property 2. You can think of it as, the third one says, if AC is equal to BC and C is not 0, then A is equal to B. This is called the cancellation law. It allows us to divide both sides of an equation by the same thing as long as that thing is not 0, and the equation will be maintained. Or if A times B is the same as 0, then either A equals 0 or B equals 0 for both. This is called the zero factor property. And I want to emphasize it is called the zero factor property, which means it does not work if the side is not 0. So if this is a 2 or a 5 or a 13, you can't split things in any predictable way. Okay? So emphasis on 0. If, say, 8 times B equals 5, there are an infinite number of things that A, B can be. And pick B to be any number and pick A to be that number divided by 5. There's an infinite number of such pairs that you can create, and they will all satisfy that equation. The other one where you can say it has to be this or both, and say that for sure, is if there's a 0 on that side. This is called the zero factor property. So this is a property of equations. We can add something to both sides of an equation, and the equation will be maintained in the sense that the solution set will be maintained. We can multiply both sides of an equation by the same non-zero entity, and the solutions will be maintained. We can divide by the same non-zero number, and the solutions will be maintained. And if we have a product of two expressions equal to 0, one or the other expression must be 0. So like I said, these are things that can be proven, but we're not going to prove them here. If any of you are going to be math majors, then in a class called Advanced Calculus, you'll prove it. So, definition. Solution. Solution set of an equation So for example, I can have x plus 1 equals 2, and I can know x equals 1 is in the solution set. Since if I replace x with 1, since if I put 1 in the place of x, that statement that says 1 plus 1 and 2 are the same thing is a correct statement. I can say that x equals 3 is not in the solution set. Since if I replace the x with 3, that is an incorrect statement. It is not correct to say that 3 plus 1 is 2, based on our rules of arithmetic. Okay, so when I say solution set, that's what I mean. If any variables are present, the solution set is the values that you can plug into those variables so that when you say the statement that the equation suggests, it becomes a true statement. Anything for which the statement becomes false and is not true that the left side and the right side give you the same thing, we say these are not in the solution set. So when you are asked to solve an equation, what you are asked to find is the solution set. You need to find all the values of the variables that make the equation true. And oftentimes, these 4 properties that I just wrote on the board is what's going to help us figure out those values. To solve an equation, needs to find its solution set. Find the set of values for the variables that make the statement true. Okay, so now let's talk about solving equations. That's what equations are. This is what it means to solve them. Now let's talk about the process of actually solving different equations. We'll discuss 2 things separately. Solving linear equations and nonlinear equations. Where we will emphasize some special cases here. But we'll also talk about some general approaches to solving nonlinear equations. Okay. So let's start with linear equations. Linear equation in the variable x is one of the form, or one that can be written in the form ax plus b equals c, where a is not equal to 0 and a, b, c are constants. Now remember what our constants are. Those guys for us pretty much just the real numbers usually. Members of the real numbers. Which is going to just be the main set that we're looking to find our domain elements from. Usually it's going to be a subset of the real numbers in this class. So once you have an equation that can be written in that form, you say you have a linear equation. So 2x plus 1 equals 3, or 0.5x plus radical 2 equals 17, or whatever. As you can substitute anything, you can even put in 0 here, 2x plus 0 equals 0, right? And you can put in any set of numbers for a, b, and c, just making sure that the a is not 0 itself, and what you will obtain is called a linear equation. to solve linear equations. Use properties 1, 2, and or 3 to isolate the variable. We spoke about PEMDAS before. PEMDAS must be respected. And kind of something that's intuitive to a lot of people, but I don't know if it's ever been stated to you, so I'm going to state it. And it's very intuitive, so I'm not even sure how to state it in words myself. Our attachment operations, while addition and subtraction are separation. Operations. That's not an official thing. But this is just some intuition that might help here. So in other words, if I see something like this, x plus 1 equals 5. Then I kind of think of the 2 as being attached to the x, while the 1 as being separated from the x. I will think of these as two separate terms. Right? So I think of this here as one term, where 2 is attached to x, and this is a separate term. So whenever I see things like that are connected by a multiplication, I think of them as being attached. They're kind of one guy until I intentionally sever them using a division operation to undo the multiplication. Okay? And you can almost think of these two as inverses, right? Like you can use a division to undo a multiplication, you can use a subtraction to undo an addition, but the addition separates things. If addition is between things, you can think of it as two things. Whereas if something is being multiplied, I can think of that as one thing. Understand? So that might help you. So when it comes to PEMDAS, the idea is when you're trying to isolate something, you want to get rid of the things that are separated first and get rid of the things that are attached to last. Okay? And you do these by performing inverse operations. So the inverse of a multiplication is a division, the inverse of an addition is subtraction, and vice versa. Okay. So PEMDAS must be maintained. You can think of multiplication and division as having things attached. addition and subtraction as having things separated, and you kind of want to isolate a variable by getting rid of separated parts and getting rid of attached parts afterwards. And just make sure PEMDAS is always respected. So if anything is in parentheses, you deal with that first. Anything's raised to a power, you deal with that first, etc. Second, etc. Okay, so let's maybe do some examples. And I feel like I have way too many examples for linear equations because they're not exactly the hardest equations in the world to deal with here. But let's deal with some quickly anyway. So those are all linear equations, and I pretty much told you everything you need to know to solve them. And I don't assume many of you have problems with these, but let's just be careful. So remember, the goal is to isolate the variable. And by that I mean isolate it on one side of the equation. So for these guys, you want to end up with something like x equals blah, right? Now that statement will be your solution, quote unquote. Okay, so isolate the variable, meaning the guy that's not obviously a real number, it's just a letter here. We want to isolate him, get him on one side of the equation by himself. What we're going to do is we're going to use inverse operations to isolate it, and we will do that by taking advantage of properties 1, 2, and 3 as said before. So, go through A, for example. So if I say 2x plus 1 equals 5, and I want to know what x can be, what we can do is, notice that the 1 is separated. What I want to do is I want to get rid of that first. I will do it by adding the same thing to both sides of the equation. Namely, I will add -1 to both sides of the equation, because if I take a positive 1 plus a negative 1, that will give me 0, and he will be erased from that side. So I would end up with 2x equals 4. Now, what I just did was I actually subtracted 1 from both sides. Or you can think of it as adding a -1 if you want to maintain the language used in property 1. And so that would be the first step. I got rid of the thing that was separated from the x. Now, the 2 is attached to the x via multiplication. I can undo that attachment relationship by doing the inverse of the multiplication. So I can now, instead of multiplying the x by 2, I can divide the x by 2. But because it's an equation, property 2 says, well, property 3, I think, would say I would have to do it to both sides in order to maintain the equation. So I end up with x equals 2. And what I did, which I'm not always going to write, and I suggest you get out of the habit of actually writing this yourself, is I would divide both sides by 2, so that based on what we learned about rational expressions, those would cancel, and then this can be reduced. And so I would end up with x equals 2. That looks like a statement like this, therefore, that is my answer. And you can always check that if I plug in that value for this variable, this becomes a true statement. 2 times 2 is 4, plus 1 is 5. And notice that I have to do it in that order because of PEMDAS. I would do the multiplication first and the addition second. Okay, so x equals 2 is that solution there. B. We're in a similar situation, except the variable that we want to solve for is in several locations. He's over here attached to a 3, and he's also over here attached to a -2. To isolate the variable means we want to get all the variables on one side, and so I can use properties 1, 2, and 3 to get this done. So what I can do is I can add 2x to both sides. That'll give me a 5x. And he will be removed from that side. And then to isolate the variable, now I'm in this situation, I can just remove that guy by subtracting 5 from both sides. Now we have a 5 attached to the x by multiplication. I can undo that by a division. And 15 divided by 5 is 3. So x equals 3 would be that solution. And you can check. 3 times 3 is 9, plus 5 would give you 14. If I plug in 3 here, 2 times 3 is 6. So this is -6, 20 minus 6 is also 14. So that statement is true if my x is equal to 3. Okay, someone help me do C quickly, so we can get to something more interesting. How do we do C? Yeah. So you would add 1/2 to both sides. Okay, and what would that be? What's 2/3 plus 1/2? Come again? 7/6. 2 times 2 is 4, plus 3 times 1 is 3. All over 2 times 3 is 6. So that gives us 7/6. Now how do I get to the x? Huh?
Multiply 4/3.
I can multiply by 4/3, which is the same as dividing by 3/4. Right? But we know what that means, flip and multiply. So I'd multiply both sides by 4/3. So on this side I'd be left with x. And on this side, we'd reduce first. So we get 14/9 would be the solution there. Another way to deal with equations like this, which there were equations similar to this on the test. Well, a little bit more complicated, but the idea holds the same. Another way here, you can do what we call clear the denominators first. So that'll save you from having to deal with fractions in like most of the steps. What we can do is clear the denominators means we can multiply both sides of the equation by the LCD. That is legal because of property 2. So I could have taken 3/4x minus 1/2 equals 2/3. What's the LCD here? Huh? LCD would be 12. Alright, that's guys 2 squared to the first 3, so it's 2 squared times 3 would be the LCD. And so what we could do is we could apply property 2, and I could multiply both sides by 12. Distributive law would take effect here, and what would happen is the 4 would cancel into the 12, and I would be left with 3 times 3, which is 9x. 12 times 1/2, the 2 would cancel, I would get 6. This 3 cancels into that 4, I get 8. And And so now I have an equation without fractions in it, just by multiplying through by the LCD, which is a lot simpler to deal with, especially if you're not good at adding fractions quickly in your head. And even if you are, it's nice to be in a situation where there's less risk of making a mistake if you're rushing, you know what I mean? So now we can add 6 to both sides. So 8 plus 6 would be 14, and so we get x equals 14 over 9, which we got before. But this might be another way of getting there, which is probably a little bit easier, especially if you don't want to risk making a mistake with fractions. So that's a strategy you should be aware of, clearing denominators. So if you have a bunch of fractions all over the place, you can actually multiply through by the LCD of these fractions, and you get an equation in a little nicer form. You can look at D. I'll redo this one. Yep.
Move the 0.6 over.
And move 0.6 over. So we subtract 0.6 from both sides, and what would I get over here?
0.6.
You also get 0.6. So now 0.4 is attached to the x. We can divide both sides by 0.4 to remove that. How do I divide 0.6 by 0.4?
Would that be 6 over 4? Or
Right. So if you have decimals, what you can do is you can move them, the decimal places, the same number of places in the top and the bottom, and that equation will be maintained. Because essentially what we just did is we multiplied by 10 over 10. So this is pretty much, this is the same as 6 over 4, which I can reduce to 3 over 2. Or 1.5. There is another technique that could help out with something like this. Not quite clearing the denominators, but you can clear the decimals. So another way, especially since a lot of the things you're not allowed to use calculators on quizzes and tests, so if you have any little trick to make the mechanics of the problem easier, you should probably pay attention to those. So we could actually clear the decimals. You would do that by multiplying both sides again, which we can do by the second property. By 10 to the nth power, where n equals largest number of decimal places that appear. That's a fancy way of saying I can move all decimals in all terms by the same, if there's no parentheses or anything to worry about, everyone's kind of spread out. I can move all decimals in all terms by the same number of motions, either to the left or the right. So if I have 0.4x plus 0.6 equals 1.2, notice there's one decimal place here, one decimal place here, one decimal place here, therefore n is 1. So I can multiply both sides by 10 to the first power, so I'm multiplying this entire equation by 10 on both sides. Multiplying by 10 simply moves all the decimal points one place to the right, whereas dividing by 10 moves them to the left. So this will give me 4x plus 6 equals 12. So this gives me 4x equals 6 by subtracting 6 from both sides, which now gives me x equals 6 over 4, and so x equals 3 over 2. So a couple of tricks there, and we'll work on some more complicated equations soon, kind of like what we're on the quiz. But you'll see all these little techniques that we're using in the easy case here. They'll come into play in more complicated cases as well. So it's good to again know how everything works in the easy case, because the complicated cases are exactly the same thing. They just look scary. They're not scary. They're not different. I had 21, so that's supposed to be 20. Yes, it is a 20. What do we do here? Distribute first because of PEMDAS. PEMDAS says figure out what's going on in the parentheses first, but this is pretty much as simple as you can get. These are unlike terms, can't combine them. So we move on to the next one, which is multiplication. Because on this side I have a subtraction and multiplication. Multiplication comes before subtraction. So the first thing I'm going to do is apply this multiplication and expand the parentheses. So that would be the first step. Second step would be combine like terms. Now we're in a very similar situation to the very first example. Get rid of the 3 that's separated by subtracting 3 from both sides. And so I'll get 18 over here. Now get rid of the minus 6 that's attached by dividing both sides by minus 6. Get x equals minus 3. So that's pretty much linear equations. If you have anything too crazy going on, just use PEMDAS to separate everybody. Combine like terms. You'll eventually get to a situation that's like the simplest case, and you can move on. Now, of course, what defines a linear equation, you'll notice that the variable only appears to the power 1 or the power 0 if it's not attached to the other constant. Let's talk about nonlinear. Now, I'm going to split these into some special cases. You can have a nonlinear where, and nonlinear just means it doesn't look like a linear equation. So sometimes it's not linear, but everywhere you see the variable, it's in a like term, meaning it's the variable to the same power. So, for example, squared equals 4. Another example, 2x cubed equals 8 minus x cubed. So these are not linear because the x is raised to a power. It does not fit the form of a linear equation. But the variable is in like terms everywhere it appears. There's only one kind of operation working on the variable. And in this case, isolate the variable. As in the linear case. Then raise both sides to the appropriate power. And that's, the raising both sides to a power is kind of like applying property 2. So it's because to get, like say if I wanted to turn this in x cubed, I could multiply both sides by x. But since my x squared is equal, my x would be equal to 2, I can multiply by x on one side and 2 on the other side, and it kind of looks like I'm raising both sides to the same power. But what's really happening is I'm applying property 2. Then raise both sides to an appropriate power. if possible. It's not always possible. So for example, if one side is a negative number, raising it to the power 1/2 would not be possible, because we know that we can't have a negative power in a radical, in an even radical. But as long as it's possible, you raise it to the appropriate power. To obtain x on one side. So again, the example, at x squared equals 4, my x squared is isolated, but I want to get x. So what I can do is I can raise both sides to the 1/2 power. Now the thing is, this can get a little sketchy because there are some times when you have to know how to change signs. So this is the disadvantage of this method. It's possible sometimes to introduce well, they're called extraneous. Let's call them fake solutions via this method. And we'll see examples of that. We'll see some situations where it seems like the appropriate thing to do is to raise both sides to a certain power, but you realize sometimes by doing that we introduce solutions that shouldn't be there. And so we kind of have to be careful here, and we have to make sure, check your work after applying this rule. But if you kind of know what you're doing, you're experienced enough, you can get away with doing something like this. The second way I would prefer in general, if possible. But let's do this example, and then I'll talk about another way to solve nonlinear equations. Example. So here our variable shows up in several locations. However, notice it's raised to the same power in all locations, so it's in like terms in these locations. So what I can do is I can isolate the variable just as in a linear equation. So I can add x cubed to both sides. And so I have 3x cubed equals 8. So now this 3 is attached to it. To get rid of it, I can divide both sides by 3. And then I can raise both sides to the 1/3 power to obtain x equals 2 over cube root of 3. Now, when you raise something to the 1/3 power, you do not need multiple signs. It would only be a positive thing. So you could think of those as rules, that would be fine. If you're raising something to 1 over an even number, first of all, that thing must be positive. And if you're doing that in an equation setting, you must have 2 signs to worry about. If you're raising something to 1 over an odd power, it will keep the sign of whatever is there. So if this was a negative, the negative would still be here. So that's one situation. There's another situation. Sometimes the variable can appear in unlike terms in several locations. So these are nonlinear equations. They do not look like straight line because our x's, they do not look like a linear equation because our x's have powers other than 1 and 0. You will notice also that x shows up in several locations, and in this first equation, it's in unlike terms because this one, the x is raised to a 2. Over here, it's raised to a 1. Here, x up here is raised to the third power, the second power, the first power, and the 0th power. These create unlike terms for the x value. Now, when you're in a situation like this, and this can also work in the previous situation, by the way. The preferred method would be something called solving equations by factor. And this method has the following steps. Bring all terms to one side so that it doesn't matter, but for definiteness, let's just say the left side. Left and right can be switched everywhere here. Okay. But let's just say, okay, you choose to move everyone to the left side so that the right side is 0. Step 2 would be to factor the left side. And after lecture 2, well, after the last lecture from last week, we pretty much know how to factor random things now. So that shouldn't, step 2 shouldn't really be a problem. And 3, you apply the 0 factor property. And 4, sometimes the factors themselves, you might get linear factors, but you might also get nonlinear factors. And so you pretty much rinse and repeat. And this is called the solving equations by factor. So let's do an example here. Solve that first one. So you'll notice that the variable appears in several locations in unlike terms. Step one, bring everything to one side, right? We are allowed to do that because of property 1. So I can move this x to the left side to become plus x. So move everything to one side so that there's a 0 on the other side. Now, the next step would be to factor the left side. What is this factor to?
X plus 6, x minus 6.
Come again?
X plus 6, x minus 1.
That doesn't work because this is 6x minus x does not give you positive x. Huh? So after you factor, do that little check. Remember, the sum, the product of the two inner terms added to the product of the outer terms must give you the middle one. So now I have a multiplication of two expressions giving us 0. This puts us in the zero factor property, the realm of the zero factor property. This means that either this one is 0 or that one is 0. Now, once we do that, we're now in the realm of a linear equation in both cases. So now I just follow a previous method that we mentioned. The linear equation method works here, in which case I will just isolate the variable. So x can be this, or x can be that. It's good if you check your answers. Sometimes it's not that hard. It's just a quick, just to look quickly and see. Check how these work in original equation. Right? Just as how you can check yourself to see that you factored correctly. Once you get to an answer, you should quickly be able to check that they will actually work. So for example, if I plug in -3 here, I would get +9 minus 6. So this side would give me 3. If I plug in -3 here, I get minus a -3, so that side gives me 3, so that works. If I plug in a 2, 2 squared is 4, minus 6 gives me a -2. If I plug in a 2 here, that also gives me a -2. So that works. Both sides of the equation give me the same thing, so therefore these are in the solution set. My solution can be either of those two numbers. In this situation, everything else is already on one side, so we can jump to step 2, which means to factor this side. How would you factor something like this? By grouping. So I see there are 4 terms, so I probably think by grouping. So I'll think of these 2 pairs together, and what would I factor out? X squared, that's the GCF over here, and over here, we made -1, that would be the GCF over here. I'll notice that x plus 2 is left over in both situations, so that's a common term, I can factor that out. Now, I could apply the zero factor property right here, and I will just have a nonlinear equation to deal with here, which I could do, but it's nice to just factor as much as you can to, 1, avoid mistakes, 2, make sure you flesh out all solutions, because if you jump the gun, you can end up making mistakes here. So the zero factor property would say that either this or that is 0. I know the zero factor property has 2 things in it, but you just understand that you can extend this to several things, because you can think of this as one thing and that as one thing, so this equals 0, and then you apply the zero factor property again to this, and so you can eventually get any length of multiplications equals 0. You can set each one equal to 0. So we have x plus 2 equals 0, or x minus 1 equals 0, or x plus 1 equals 0. So we can have x equals, now all of these are linear, we know how to do with that. So it's -2, or x equals 1, or x equals -1. So those three form our solution set. Our solution set here has three things in it, and of course, show us do a quick check of your answers. Now I want to do another special case that it shows up often, as well as there are some techniques that will be useful for us in the future, and that is solving quadratic equations specifically. So we're still in the section solving nonlinear equations. We specifically want to single out quadratic equations. Definition: a quadratic equation in the variable x is one of the form ax squared plus bx c equals 0, such that again your a is not 0 and your a, b, c are constants. The equation of this form, they can write in that form, is called a quadratic equation. Now there are three main ways that we can go about solving quadratic equations. One, solve by factoring. Our first example in the last section was like that. Bring everything to one side, factor it. Now, if your a is 1, we know how to do that. If your a is not 1, we can use the AC method or the trial and error method to get it to factor. Now, hopefully it can factor, and that would be kind of the first thing you would try in general. So solve by factoring is probably the first thing to try. To try. Second, you can solve by what we call completing the square. And even though I put this second, it's pretty much the last thing to try. The third thing is using what we call the quadratic formula. Now, I put this in step 3 for historical reasons because this formula is actually proven using this technique. So technically completing the square comes first, but it's kind of not really something you want to do unless you have to. It is important in other situations though, so we will talk about circles pretty soon, and there are some other cases in which completing the square is a very useful technique. But when it comes to solving quadratics, pretty much always going to try factoring or a quadratic formula. Unless you're specifically asked to do otherwise, which will be very rare. So do some examples. So we won't finish this today, but there are 4 more things I want to talk about in the solving equations section. So after this, we're going to solving equations with radicals, solving with absolute values, solving with rational expressions, and then we'll talk about identities and contradictions. But let's finish this guy, or get as far into this as we can. So again, the first thing we try is solve by factoring. We just want to factor the left side, and then use the zero factor property. Does this factor?
Yes.
To what? Plus and plus. So then we can get x equals -3 or x equals -2 as our solution. So that one wasn't so bad. What about this one?
Negative.
Move it to one side. Now, let me make sure to state here, common mistake. Sometimes students will see this and they realize, oh, there's an x in each term. I can just divide both sides by x. This is incorrect for several reasons. For one, you would notice that x equals 0 is a solution to the original equation. And so dividing by x is potentially dividing by 0. Two, whenever you do something like that, you actually lose some information. And you might actually lose solution in the process. So it's very important when you have this kind of scenario, you follow the strategy that we had earlier and move everything to one side and factor. Don't start dividing stuff and doing all that other stuff, treating it as if it's a linear equation. It's not a linear equation. Strategy, move everything to one side and factor. Right, so this is a GCF factoring works here. 5x is a common term, and with x -4 would be left over. And so we apply the zero factor property here. So this means that 5x equals 0 or x -4 equals 0. And so x equals 0, which tells you, right, you would have trouble dividing by it, or x equals 2. Common mistake, don't do it. It's not a strategy for the nonlinear case. Okay, we'll stop there. We'll pick up with this and do some more on equations next time, which is on Monday. I also have quizzes to give back, so